welcome to class of satellite and radar system. So these are the contents. What is satellite? We'll study about electromagnetic spectrum and Kepler's laws of planetary motions. And finally, orbital effects and communication system performance. So first of all, what is a satellite? This is just a brief review of what we have studied in our first lecture. We'll give it a short while, then we'll move forward to where we have left from. So a satellite, we know that satellites are mirrors in space. So a satellite is a solid object, we can call it an object, which revolves around some heavenly bodies due to the effect of gravitational forces, which are mutual in nature. So these could be man-made satellites or natural satellite. We all know the example of natural satellite, which is moon, and man-made satellites are which we are making these days. If we go into brief history of Indian satellite communication, the first satellite that was used for communication purpose in India was Aryabhatta. It was launched on 19th April 1975. It is where we have started our satellite research. It was made and assembled by ISRO, Indian Space Research Organization. This is a dedicated organization which is working in the field of satellite communication. Now, in the year 1981, the first satellite named Apple was launched in space. This was the first Indian experimental communication satellite. So this is a little history of Indian satellite communication. Now, what are the advantages? We all know. It provides ubiquitous coverage. So it provides intercontinental and transoceanic coverage. Where laying down cables is a difficult job, satellite communication can help us solve the purpose. Now it is also independent of terrestrial infrastructure. There is no wiring, right? So when we talk of wireless communication, this requires no terrestrial infrastructure. Although signal generation to the earth station, that thing is wired. So every communication system is a mix of wired and wireless, but the most part of the communication is wireless. That's why we call it wireless communication. It provides rapid services, and the capabilities we have already discussed. So I have tried to pen down these here, which are fixed to fixed, mobile to mobile, fixed to mobile, point to multi-point. These are the facilities or the capabilities of satellite communication, which we all are using on everyday basis. Now coming to limitations or disadvantages, if we talk about satellite communication, what are the disadvantages? The initial cost of launching is high. We know manufacturing a satellite is a difficult task, is it time consuming, needs a lot of expenses, no sole body can make it. So most of the organizations are government organization that works in the field of satellite communication. Then launching is a separate process that requires a lot of space, planning, and finances are associated with it. So launching a satellite into orbit is costly thing. Although how do we compensate for the cost? We do compensate for the cost by the revenues that are generated every year by selling the satellite services. Like we use DTH services, we pay for the mobile services that we use for calling, for SMS, for using data. So we pay the service provider. That is how the revenue is earned. Now if we talk about the second limitation, there is a fixed bandwidth, and that is gradually being used up. The population is increasing day by day. Each person is using more than 2 or 3 devices. So the bandwidth is getting used up. Another thing, in case of communication, while we are talking or sending messages or exchanging information, any kind of information exchange, the propagation delay is something that must be considered. Right? So in case of satellite communication, because of the distance, the propagation delay is large. Now if we talk about the categorization, basic categorization, we have active and passive satellites. So active satellites are used for linking and also for processing the signal, whereas the linkage is known as bent pipe technology, where processing like frequency translation, power amplification, etc. takes place. So an active satellite will do all of these things. It's capable of doing all the things, that is processing the signal, amplification, translation, down conversion, up conversion of frequency. So all these are part of active satellites. Whereas if we talk of passive satellites, so they are just used to link to station through space. They are not much capable. They are basically low cost satellites. They use less of the power, and they are usually not used for your communication purposes. So when we talk about transponder, when we talk of regenerative technology, active satellites are the thing. The next thing is, whenever we are studying any kind of communication, be it wireless, be it mobile communication, be it satellite communication, be it radar, electromagnetic spectrum is something we must always focus on, because EM spectrum is the available spectrum for us, whether we use it for transmission of signal, for communication, whether we use it for different application. We first need to know what are the frequency ranges that we use for communication. So if we talk about the radio frequencies, that lies between the range 10 to the power 4 to 10 to the power 12 hertz. So this is the major spectrum that we use for communication. Now this is further divided into into parts. Now within this range there are classification that is used for particular application. Microwaves are separately studied, satellite communication is separately studied. So radio frequencies are also studied in depth. Then if we talk about infrared, it lies in the range 10 to the power 12 to 10 to the power 14 hertz. If we talk about light, it's 10 to the power 14 to 10 to the power 15 hertz. Ultraviolet rays lies in the range of 10 to the power 15 to 10 to the power 16 hertz. And if we talk about X-rays, 10 to the power 16 to 10 to the power 20 hertz. And gamma rays is above 10 to the power 20 hertz. So we must know the basic categorization. Now as per IEEE, if we classify the bands, the major bands that we these are very high frequency, these are below 1 gigahertz. These are usually used for tracking the little LEOs. LEOs is low Earth orbit satellites. L band, which uses 1 to 2 gigahertz, basically used for mobile services. L band, S band, C band, X, Ka and Ku are the bands which are mostly used for satellite communication. Here Ku is K under and Ka is K above, right? So L band is for mobile services. S band 2 to 4 gigahertz we use for mobile and navigation services. C band is mostly used for fixed services. This is the band which is mostly used, most of the applications of satellite communication. X band 7 to 8, government use in USA, Russia, Japan and various other nations. If we talk about K under 10 to 18, these are used for mostly fixed services, and Ka in mobile services, fixed mobile services, inter-satellite links. And these bands are, rest of the bands, Q band, V band, W band, are kept for future use when we'll be jumping to other bands to higher frequency range to accommodate more number of customers to for better speed. Then we'll be jumping to these higher frequency ranges. What is the importance of speeded light in satellite communication? We know that EM waves, they do travel with the same speed in vacuum as the speed of light, just 3 into 10 to the power 8 meters per second, right? So speed limit has an important effect on ability to communicate over large distance. So a geosynchronous satellite or a geostationary satellite, this is usually around 36,000 kilometers above the surface of Earth. Considering the speed and the velocity of EM wave that we use for satellite communication, a single wave link between Earth station and satellite will take about 238.6 milliseconds. So if this is my Earth station and this is the surface of Earth and this is my satellite, this single link, this path will take if the satellite is at a height of approximately this much kilometer, then this, and my signal is traveling with the velocity of light, then this single path will take approximately 283.6 milliseconds of time. Don't you think this is a good amount of time? So this causes delay. So this is a problem in voice traffic, right? So the disadvantage that we have discussed earlier about satellite communication, that is propagation delay, that is explained here. These are various radio frequency bands. We can give it a look. Below 3000 Hz, it is called extremely low frequency. Wavelength is mentioned here and waveband name, right? Then we have very long wave. Then we have long wave, medium wave, short wave, very short wave, decimeter wave, centimeter and millimeter wave. These names are according to their wavelength, and likewise microwave frequencies are called so, right? So this is for our knowledge that we should know. Now, how a satellite is placed into orbit and how do they revolve around Earth? That is the question. What are the various laws, what are the various forces that governs the movement of a satellite when they are into their orbit? So there was a scientist named Johannes Kepler. He was a German astronomer and a mathematician of late 16th and early 17th century. He gave us 3 laws of planetary motion. He has explained that all the celestial bodies, they are governed by certain laws, and these laws are named after him as Kepler's laws of planetary motion. He has defined these in 3 ways, like Kepler's first law, which is called as law of orbit, Kepler's second law, which is called as law of areas, and Kepler's third law, which is called as law of time period, right? So Kepler's first law states that path followed by a satellite around the Earth will always be an ellipse. If this is my Earth and this is the satellite which orbits my Earth, the path that it will follow around Earth will be elliptical. Although here I have drawn this at the center, which is not correct. Here it also states that path followed by the satellite around the Earth will be an ellipse, or we can say path followed by the smaller body around the larger body will be an ellipse, with the larger body or the Earth at one of the 2 foci of the ellipse. We know that one of the foci is here, one of the foci is here. So here I can draw my Earth, or here I can draw my Earth. These are the 2 foci of my ellipse. So the smaller body will always revolve around the larger body, with the larger body at one of the 2 of its foci, right? Now the eccentricity of the ellipse, which is represented by small e here, tells the path of the satellite. We know that for circle eccentricity is 0, and for ellipse there must be some eccentricity, although it will always be less than 1. So these are the mathematical things, these are associated with the path of the satellite. So the first thing that we need to keep in mind is about the first law of Kepler, that path followed by satellite will always be an ellipse. Although I'll tell an exception about it. We have discussed about geostationary satellite. A geostationary satellite is an exception to Kepler's first law, as geostationary orbit is always circular with eccentricity equals to 0. if we leave this geostationary satellite, apart from geostationary satellites, all the satellites are placed in an elliptical path. A satellite moving in elliptical orbit has two locations along the orbit. These are apogee and perigee. These I'll show with the help of a diagram. Now, period of the orbit takes time to complete an orbit. Complete on orbit is measured from perigee to perigee. So, so if this is my satellite and this is my Earth, which is at one of the two foci, with this red boundary, I've tried to show the path of the satellite, which is elliptical here. So we can see from the center of Earth, if we calculate the distance of the satellite when it comes closest to Earth, the minimum there is the distance between Earth and satellite here is minimum, and that minimum distance is called as perigee. And while moving in its elliptical path, when my satellite reaches the distance which is farthest from the Earth, at this point the distance from the center of Earth to the satellite is called as apogee. And if we want to measure this in as linear distance, then we will make the center of the ellipse, we divide it with a line which is the semi-major axis, and this is the semi-minor axis. So semi-major axis can be called as addition of apogee and perigee will give me semi-major axis, right? So period of the orbit, time taken to complete an orbit, measured from perigee to perigee. So how much time it takes to complete one complete revolution? When my satellite was here and when it takes one round and comes back here, the time elapsed can be calculated, can be called as orbital time period. That is time elapsed by a satellite to complete one complete revolution around the larger body or the Earth, right? So here it is mentioned, the satellite moving in elliptical orbit has two locations along the orbit: apogee, the outermost tip of the Earth, and the satellite is farthest from the Earth, and perigee is the closest point to Earth. So I hope the Kepler's first law is explained here. One thing that we need to remember here is apogee and perigee is always calculated from center of Earth. Kepler's second law. Kepler's second law is also called as law of area. It states that a line joining a planet or comet or our sun, or our Earth and the satellite, it sweeps out equal areas in equal interval of time, right? So here the central body is considered as sun, we can consider it as our Earth, and if the satellite is moving, the area covered is equal in equal interval of time. How is that possible? When my satellite is here, this is the area that is covered, and when my satellite is here, in dt time it covers this area. How can A1 and A2 be equal? We can see the distance is larger when satellite is at this point, right? We can see the distance is larger here, right? The distance is smaller, the distance between the satellite and Earth is smaller here. Then how to make these two area equal in equal interval of time? If I calculate it in time elapsed dt, that is the same time in both the cases, how this area will be equal? That means the velocity of satellite would increase when it comes closer to the central body, and it will reduce when it goes farther from the body, right? So this is the only way it can sweep equal area in equal interval of time, right? That means the velocity of satellite becomes high, it becomes faster when it comes closer to the central body, and its velocity decreases when it goes farther. The empirical law is discovered by Kepler, arises from conversion of angular momentum, right? Thus, a planet executes elliptical motion with constantly changing angular speed, right? The speed with which it is covering the circular motion is called as the angular speed, and it keeps changing angular speed as it moves around its orbit, right? Equal areas in equal time. Now Kepler's third law. Kepler's third law states that square of the time period of orbit is proportional to the cube of the mean distance between the two bodies, right? Time period, square of the time period, here time period is represented with capital P and mean distance is represented by small a. So these two are proportional to each other, and removing the proportionality, we replace it with a proportionality constant, which is mu here, which is called as gravitational constant, and its value is mentioned here, right? So Kepler's third law states that T square is directly proportional to, or P square is directly proportional to a cube, and removing the proportionality constant, proportionality sign, we may replace it with proportionality constant mu, right? Now after Kepler's three laws of planetary motion, let's study some of the effects of orbit in communication system performance. How my orbit, how my motion of satellite around Earth is affected, affects my communication performance, right? Solar eclipse, we all are aware by this term. We have been seeing eclipses since our childhood. So what basically an eclipse is? A satellite is said to be in eclipse when the Earth prevents sunlight from reaching it, right? Solar eclipse, what is solar eclipse? When there is no sunlight from it. So in case of satellite, what happens? A satellite is said to be in eclipse when Earth prevents sunlight from reaching it. That Earth is rotating around sun, and a satellite is rotating around Earth. So a time will come when all three are aligned in a way. All three are aligned in a way. This is our sun, and this is our Earth, and I would represent satellite with this. There will come a time when all three are in a line, in a way that Earth will prevent sunlight to reach satellite. What happens in such case? We know that all satellites are equipped with solar panels. They do gain energy from sunlight, and that energy is used for their movement. So in that duration of time, the satellite will stop getting energy from sun, and that will affect its communication process. For those time durations, satellites are equipped with high performance batteries. They do switch on, and they do they help the satellite overcome from that situation. For geostationary satellite, eclipse occurs close to equinox periods, which is around March 21 and around September 23. Even these dates are calculated. What are equinox periods? These are the times when sun, the earth and satellite are nearly in the same plane. In this period, the geostationary plane is in the shadow of the earth, on the far side of the earth from the sun. I have drawn this, right? So with this diagram, we can see satellite is in eclipse when it prevents the sunlight to reach it, and satellite in sun transit outage, right? During full eclipse, a satellite receives no power from its solar array and operates entirely from its batteries. The length of the eclipse period will vary from few minutes to over an hour. So for that duration of time, for those few minutes or then that hour, it will operate on its battery. It will switch to batteries. What is sun transit outage? During the equinox periods, not only the satellite pass through the Earth's shadow on the dark side of Earth, but the orbit of the satellite will also pass directly in front of the sun on the sunlit side of the Earth. So this is called as sun transit outage. The sun is a hot microwave source, we know that. Its temperature is close to 6000 to 10,000 Kelvin. The Earth station antennas will therefore receive not only the signal from satellite but also noise, because so much of energy, it will receive some noise also, right? Which is calculated in noise temperature terms with Boltzmann constant. We do have equations for. So that's it. Thank you.